Welcome. In this video, we cover section 3.7, the chain rule. And the chain rule is definitely the most important derivative rule that we have seen yet, and that we might ever see. It really expands the number of functions that we can take the derivative of. So let's see how it works. I'll split this lesson into 2 days. And today, I'll just look at the chain rule and we'll do lots of examples. I won't prove why the chain rule works today. In the second video, day 2, I'll give a little bit of justification for why the rule works. But for today, we're just going to dive in, understand the rule, and try to use it a lot. The chain rule is used when I want to take the derivative of composite functions, when one function is inside of another. For example, looking at the top left, I know how to take the derivative of the square root of x, and I know how to take the derivative of x cubed plus x. But what happens when x cubed plus x is put inside of the square root function? We don't have a rule yet for how to actually take that derivative. Or on the top right, I know how to take the derivative of sine x, that's just cosine, and I know how to take the derivative of e to the x. But when e to the x is put inside of sine, we haven't done that yet. We don't have rules for that. And that's exactly what the chain rule is for, taking derivatives of the composition of functions. So the first thing that we have to do is to be able to unravel a composition of functions. So for each of these 4 functions, what is the outside function and what is the inside? So the outside, that's what we call the f. The f function is on the outside, and inside of that is g. So on the top left, that looks like the square root of something complicated. I mean, not very complicated, but I would say that the f function is the square root of x, and g is x cubed plus x. On the top right, the outside function, f, that's just sine, and then inside of sine is e to the x. Now what about on the bottom left, e to the x cubed plus x? The outside function is e to the x, and then inside of that, x cubed plus x. It's a little funny to think that in the exponential function, the exponent is the argument. With sine, I can write sine, and then there's parentheses, and if I put stuff in there, I know what's inside of sine. The e function looks a little bit different. In some computer programming, you might call this the exp function with parentheses, and then you can really see what's on the inside. But that's the same as just e raised to some power. So whatever the power of e is, that's the argument of the exponential function. That's the inside. And the last example is trickier. We don't typically think of this as being composition of functions, but you can think of it as composition of functions. And your outside function would be 1 over x, and then inside of that I put sine x plus x. Okay, so here it is, the chain rule. How do I take the derivative of composition of functions? If I start with f of g of x, so I have an outside function and an inside function, take the derivative of the outside function. There's that big F prime. But look what happens. Inside of that, that's my original g of x. That did not change at all. And then you multiply times the derivative of that inside function. Let's see some examples. All right, the derivative of sine of x to the 10. The outside function is sine. Inside of that is x to the 10. So the chain rule tells me, take the derivative of the outside function. Take the derivative of sine. I get cosine. But I'm not going to write cosine x. I'm going to leave a little blank there. And what goes inside of that, that's the x to the 10. So I took the derivative of the outside, and the inside remained unchanged. Then, I'm not done yet, then I need to multiply times the derivative of the inside. So the derivative of x to the 10 is 10x to the 9. And that's the solution. That's the derivative of sine of x to the 10. Second example, square root of tangent of x. The outside function is square root. Inside of that is tangent. What's the derivative of square root? The derivative of the square root is 1 over twice the square root, but I'm not going to put x. What goes inside of that is the original inside function, the tan x. Then I multiply times the derivative of tangent. And the derivative of tangent is secant squared. Now, if you'd like to, with this square root, since there's a 1 on top, we could just write this as secant squared x all over twice the square root of tan x. Third example, e to the 5x squared. So the outside function is e to the x. Inside of that is 5x squared. Take the derivative of the outside function. Well, the outside function is just e to the x, and the derivative of e to the x is e to the x. So I take the derivative of the outside, and I leave the inside unchanged. Oh, so I have my original 5x squared still in there. But then multiply times the derivative of the inside. The derivative of 5x squared is 10x. How about some more examples? The derivative of secant of x squared plus x. The derivative of secant is secant tangent. So I'm going to write secant, leave a little blank, tangent, leave it a little blank. What goes inside that is not x, but in fact the original inside. X squared plus x squared plus x. And then I need to multiply times the derivative of the inside. So times 2x plus 1. At this point, I made a terrible mistake. Pause the video if you need to. Do you see the terrible, terrible mistake that I have just made? All right, what it is that I really absolutely need parentheses around there. So when I have the derivative by the chain rule, I'm multiplying times g prime of x, but it's this entire g prime of x that needs to get multiplied. And so in my first example here, the g prime, the derivative of the inside, is this entire expression, 2x plus 1. So I need to make sure I put that in parentheses and multiply it times the first stuff. Okay, moving on. Second example. What makes the second example tricky is that the notation just looks a little bit weird. Cosine to the 10 of x, what that really means is, so I'm not going to take the derivative, I'm just going to rewrite it. Cosine of x, all of that raised to the 10th power. What is the outside function? The outside function is just x to the 10. And so the derivative of x to the 10 is 10x to the 9. Oh, well, 10 something to the 9. Now I'll put the original inside in there, the cosine, and then multiply times the derivative of cosine times negative sine x. All right. Oh, look at this third example. Looks like I have 3 layers of composition. On the outside is square root, inside of that is sine, and inside of that is x to the 5th plus x squared. All right, let's tackle this. So on the outside, square root. So the derivative of square root is 1 over twice the square root of whatever. And I put this entire inside back down in there. So the sine of x to the 5th plus x squared. There we go. And now what happens? I need to take that inside and take its derivative. Take the derivative of that. And it's like a whole new chain rule problem. So the derivative of sine, now sine is the outside, and so the derivative of sine is cosine, but the inside is unchanged. That stays x to the 5 plus x squared. And then finally, that function, that inside stuff, needs to have its derivative taken, and I get 5x to the 4 plus 2x. Are you screaming at me that I made a mistake? You should be. That absolutely needs parentheses right there. So I've done several examples. Now it's time for you to try. Look at these 4 problems. Do your best. Really stop the video, give them a try, and then start it up again when you want to check your work. Go to it. First example, 20 x to the 4 plus x squared to the 19th times 4x cubed plus 2x Second example, derivative of tan is secant squared. So secant squared of, inside stays the same, e to the 4x. Then the derivative of e to the 4x is 4 e to the 4x. Third example, the e function stays the same, so e to the sine x plus x to the 6 plus 7 times the derivative of all that stuff that was in the exponent. So I'm going to just start with my parentheses already. Cosine x plus 6x to the 5, and the derivative of 7 is just a 0. In this last situation, this one, oh yeah, it's a little bit tricky. Let me just rewrite it first before taking a derivative. And I'm going to call this x to the 8 plus cosine x, all raised to the negative 1/2 power. Now, when I take that derivative, the negative 1/2 comes out in front, negative 1/2, and the inside stays unchanged. Subtract 1 from the exponent, negative 3/2. Then I need to take the derivative of that inside. 8 x to the 7 minus sine of x. There we go. One more page of problems for you to try. Pause the video, give it a try. Okay, let's see how these went. e to the x, so there's my original, but then I need to take the derivative of that exponent, and so I get e to the x. There it is. Second example, the big square root on the outside, that's the outside function, so I'll take the derivative of that. That's 1 over twice the square root of, and the inside stays unchanged, so x plus square root of x. But then I need to take the derivative of that inside, and I get 1 plus 1 over twice the square root of x. Third example, the outermost function is sine. Well, this looks like another one where I have 3 levels. It's like peeling an onion. Start with the outermost layer and work your way in. So the derivative of sine is cosine. And all that stuff stays the same. Secant of the square root of x. Then let's take the derivative of that times the derivative of secant is secant tangent. So secant square root of x tangent square root of x times, now this inside function, it's a little bit weird, right? It appears in 2 places. And I take the derivative of square root, and I get 1 over twice the square root of x. Last example. This function, what is the outermost function here? Well, the outermost function is really x raised to the pi. And so the derivative of that, the pi comes down out in front, and the inside stays the same, e to the x. And then subtract 1 from the exponent. But then I need to multiply times the derivative of the inside, and the derivative of e to the x is just e to the x. But look at what happens. There really is something interesting going on in this particular problem. Because what is e to the x to the pi minus 1 times e to the x? Well, if I have any number, a, to the, m minus 1 times a, what is that? That just adds 1 to the exponent. That's a to the m. And so by the same kind of reasoning, I get pi times e to the x just up to the regular pi. There we go. Oh, but wait a second. You might have noticed that exponents multiply when they're stacked on top of each other like that. So this is really just pi e to the pi x. And I could have started my original problem as asking for the derivative of e to the pi x. And so it does give us this rule that we've seen before. The derivative of e to the pi x is pi e to the pi x. But in fact, this kind of gives us a proof. Previously, when we proved this rule, we kind of said, well, it works for 4, the number 4, e to the 4x, and we showed how this comes about if you use the product rule. But that little proof that we gave didn't work for any real number. It only worked for positive integers. But now that I have the chain rule, you kind of get maybe a hint of why this e to the kx derivative rule works when k is any real number. All right, so I will stop there. If you need to, go back and review the chain rule and going through some of these examples. It's definitely the kind of thing that takes practice, and we will do more practice in class.